All right, we are recording. So, hi, I'm Brandon.
My name's Andre.
I'm Eli.
I'm Jed.
So let's jump straight into it. Go ahead and share my Google Chrome here. So for my play exercise for 3.11, I decided to do number 9. And it says to prove the identity, and then it says cosine the hyperbolic cosine of x plus the hyperbolic sine of x equals e to the x power. And it's just a proving question, already gives the answer, you just have to say why. So the formula for the hyperbolic cosine and sine are shown right here. For cosine, it is e to the x power plus e to the negative x power all over 2. And for sine, it is e to the x power minus e to the negative x power over 2. And so you just plug that in for each one here. So instead of saying hyperbolic cosine of x, you just plug in that formula and then set it and just solve it. Which when you combine the fractions, because it has common denominators, and then cancel whatever cancels, and it equals e to the x power, which is what is given, so I know that it's right. Nah, that was it.
Alright. Looks good.
Like it.
Um,
It's good.
so next I had the number 31 for 3.11 play. Let me share my screen. Alright, whoops. So the problem is find the derivative of the function x, the hyperbolic sine of x minus hyperbolic cosine of x. So that was honestly pretty simple. I just took from the notes that we had the hyperbolic, the derivative of both of these hyperbolic sine and cosines. So brought it down to x cosine h of x, and then subtract negative sine h of x. And I mean, really, pretty much that's it. The only thing I had a question about was like whether I keep this x in front of the cosine one there. Do you guys know if I should keep that or if it goes somewhere during the thing?
You can just keep it. That's what I did. I just kept it.
Okay.
I'm
Yeah.
pretty sure it's the same. I believe you can move it into the cosine. I honestly don't know how, so I just left it like that too.
Yeah. So that was the simplest form that I could get it down to. So it was pretty simple question.
Yeah.
All right. I can share mine. Let me see. Okay. So I did number 1, which was, hold on, let me look up the question for it. Basically, it just wants for me to find the numerical value for each expression. And so for that, I took sine hx equal, and then basically that equals the e to the x minus e to the negative x over 2. And then you take it and you set it equal to 0. And so just plug the zeros in and it comes out to equal 0 because it's 1 minus 1, it comes out to 0 over 2, which is just 0. And I did the same thing for the cosine, except instead of a minus, it's a plus. And so it actually comes out as like 1 plus 1 over 2, so it's 1.
Yeah,
That sounds good.
Yeah.
Right.
Alright, so I did question 23, which is the whole find each of the following limits of the whole hyperbolic functions. Here, I did the math for each. Basically, as we know, like tan is always sine over cosine. Sine is this little e to the x minus e to the negative x over 2. Secant is just the opposite of cosine, so it's going to be 2 over e to the x plus e to the negative x. Just proved each of them. And like I even had little graphs to help see where up.
Yeah, so you could just follow each one.
A lot of them are like basically the same thing. They always go off into infinity.
Yeah,
Yeah.
that's a
Depending
good
on
way
what
of
you're trying
doing
to
that.
find.
Yeah. I just used the graphs. I didn't write out any of the like the actual math for it. I just did the graphs.
Alright. Well, that works too. I mean,
Yeah, I
Stuart
mean you get the same
was
thing.
playing with the Desmos. So.
Yeah. Yeah, Desmos is very handy, especially during like this.
Yeah.
Awesome. So now on to apply, which I did for 3.11 apply. I did number 48. Let me share my stuff. So 48, it gives this function, I guess, of the arc in St. Louis, and then it asks to for A, graph the central curve. B, what is the height of the arc at its center? C, at what point is the height 100 meters? And D, what is the slope of the arc at the points in part C? So for A, I just use Desmos because I'm not very good at freehanding graphs. And this is what that looks like. I tried to limit it just to within the range that it asked for, because it asked to graph the central curve, which is, I have it right here, which is just negative 91.2. X is going to be greater than that or less than or equal to 91, positive 91.2. So didn't really pan out here, but basically it's just where the zeros are. And then the central curve's just this, and it doesn't go down at all below the x-axis. And B, the height of the arc at its center, which is right here, the vertex. So I used this right here. I put down 190.53 meters because that's what it gives you on Desmos. Just my graph right here. Literally just the point right here. I should have marked it, but basically the height here is when the x value is 0, so you can plug it into your equation if you want to. I just use Desmos just right there to get an exact point. And then here. C, at what points is the height 100 meters? So that was pretty simple. Back to Desmos, 'cause that's how it is. So whenever the height is 100, so the y value is 100, what corresponding x's are going to be there, which obviously is going to be 2, which is going to be negative 71.558 and positive 71.558 for the x values right here for the height to be 100 meters. And then I have just some basic stuff down just to show like what I did, but I just used Desmos. And then D, what is the slope of the arc at the points in part C? That's where you need to find the derivative of this equation, which is just right here. I have it written out. I ran out of room because this number is very long. So I used the derivative rules for hyperbolic functions to figure this out. and then I plug into my derivative equation my x values to get what the slope is at that point. So there it is, which is negative 3.6 and positive 3.6 with a long decimal after it, but that's the rounding of it. And that's 48.
All right. Nice. Yeah, Desmos pretty much carried that one, huh?
Yeah, definitely.
Yeah.
I mean, otherwise you'd have to plug in like a bunch of different numbers, and I was in a bit of a rush.
Yeah.
Yeah.
It helps though to be able to see it all, like, because it gives you the points sometimes too.
Yeah, yeah, it does.
All right, so I did number 49 for my 3.11 apply. So basically the question is just, it gives you this whole equation here, which is the water wave length or the velocity of a water wave according to how deep the water is. And then it explains some of the variables here. And then what it's asking is, why would this other equation be appropriate if the water is really deep? So basically, I just wrote kind of like an explanation here since there weren't really numbers involved too much. Just basically that the difference between these two equations is going to be that the hyperbolic tangent of this quantity over here is going to go away. And that's going to because the deeper that you go, your d value is going to increase according to the length of the wave, which is going to then cancel out this entire hyperbolic tangent function so that so like I wrote here that it's going to be irrelevant. So it's going to just be that you have to worry about in order to calculate the height of the wave or whatever it was, or the acceleration of the wave. So yeah.
That looks good.
Yep. I also did 49 and pretty much did it the same way. I think I just explained it in a couple less words. So right here, I did draw a little picture to help show it. But basically, I said as x approaches infinity, the tension hx approaches 1. And so basically, what that means is as the water gets like really deep, the equation would change because that would change to a 1. And so I showed that right there. And so basically, you're getting the change that it wanted you to prove. Yeah.
Yeah. And to add to that, the way I figured out it was going to 1 is I just like plugged in like higher and higher numbers and like realized it was just getting closer to 1.
Yeah.
So yeah, realized that that second part didn't really matter.
A little
Cool.
off topic, but I wonder if they can use this to do like for like tidal waves, you know, for like a warning of like there's a big wave coming, everybody leave.
Oh yeah.
You
I
know,
don't
like
know.
the tsunamis.
Yeah.
Yeah. I'm sure they do.
Yeah, I mean these are apply examples are usually pretty good at using like real life examples in like a specific environment.
Yeah.
Yeah.
All right.
Way to show us that our math isn't just random numbers, that we're going to use it.
Yeah.
Yeah.
I
All right.
did 48, same as I guess like we both did the whole graph on Desmos. I just showed my little screenshot of it. Then the height of it, you can either plug x as 0 into it and you'll get the same, the 190. Let's look at the top point right. Then for the points at the height equals 100 meters, I did the, I guess what's it called? Analytical approach of it. I just plugged 100 for y and then solved for x. Which I still got the same 71.558 and then 71 since it's symmetrical along that x-axis. Or sorry, y-axis.
Yeah, that's the y-axis.
And then the slope at the points, I'm pretty sure I did the math wrong because I couldn't get my sine. I couldn't get my calculator to work for the sine part of this. I'm not sure what was wrong with it. I did the derivative, which got me this big old long mess of decimal numbers. And I plugged in positive and negative 71.558 for my x. Got like the slope at positive x is a negative this small number, and then negative x is a positive number since it's going up and it's going down.
That looks good. Did you actually get your Desmos graph to only graph like in a specific interval?
So I just had it. I just typed in the normal thing. Yeah, I just typed in that, and then
Oh,
I
okay.
just shrunk the graph. So like, say if it was x equals 4, and I only want like few numbers in it, I would like shrink it in this way and only show like 6 through 3.
Oh, okay. I wonder, can you even graph like a graph on a specific interval in Desmos or no?
I could see if you do like squared
Yeah.
4, I put a c in there. I think if you do like so we only want from like 4 this to 2. I mean, like it kind of sort of shows it, I guess.
Yeah, but yeah, I mean, I was talking like the actual yeah, like the graph itself would stop there.
Yeah, she's already like I've seen some new stuff from Desmos that I didn't even know it could do that she's like shown us in class. I was like, what the heck?
Yeah.
Yeah, I just use it for this part. I don't know how to do the rest of it.
Yeah. It's cool that it's also like a calculator too. Like it can calculate stuff. All right, so now we're on 4.1.
Yeah.
So for my play, I did number 1. Let's see if I can share. Awesome. Here we go. So number 1, just asked to explain the difference between an absolute minimum and a local minimum. So this wasn't like a difficult thing to do at all. Like it doesn't really even like relate to any of our learning objectives, but I thought it was so like important to know like this difference. So I wanted to put in our discussion. So the absolute minimum is gonna be like the lowest. I believe it's like the lowest horizontal tangent on the graph, like the lowest point where the slope is 0 on the graph, and then the local minimum is where it's not like I guess it could also be the lowest point, but it's only in like a specific area that is relative, which is what I put in to like a relative point, like relative to like there's nothing else to like to the left and right, it's just like right at that spot is how I kind of worded this, which I believe that's right.
Yeah.
Yeah.
Yeah. I did the same one. I tried to remember exactly what she said, like how she worded it in class. And as far as the absolute minimum, that one was pretty easy because it's really just the hold on, let me share my screen really quick. Yeah, so the absolute minimum is just going to be like the lowest point as far as the whole graph. Like corresponding to the y-axis. And then your local minimum, I remembered what she said in class was where you can like look to the left or the right and not see anything that's going to be like less than that. So, I mean, yeah, but you said the relative minimum, and I just said on a particular interval. So, basically,
Yeah,
same
it's
thing.
the same thing. Yeah.
So, yeah.
So yeah, I also did that one, but I do think I messed up my definition of an absolute or of the absolute minimum because I said, oh, there's the wrong one. Hold on. Here we go. There it is. Okay, so I said it's the smallest point over the entire domain of the function rather than at like the last like or the lowest critical point. Then for the local minimum, I said it's like the lowest point in a certain section of the function, usually seen at some critical point, which would be, which yeah, the critical. It wouldn't be like every critical point, but definitely certain critical points where it has the like dip. You know what I'm saying?
Yeah.
Yeah,
And
that's a good
your definitions sound right. I would keep that. That's fine.
Okay.
Yeah, I think it's good that you added the critical point in there because
Yeah.
like we also look for those in different problems, and usually they occur like that when there's like a curve change.
Yeah.
Yeah.
I just noticed that it like might make it seem a little bigger.
Yeah.
I like your guys' maximum. I think we can all agree on that. I think the minimum, I would rather say it's just a dip in the graph. Like if you're looking at what's it called? We're looking at like a wiggly line. It's just any sort of dips that have concave ups.
Yeah.
Yeah.
If I did question number, oh shit, question number 4, and we'll take a look at this little graph here, which I redrew down here very artistically. And then we had to state, you had to state whether the points A, B, C, D, R, and S are absolute mins, maxes, local mins or maxes, or neither. See that? I'll just take a look at this. This is much more clear. So looking at A, I said that would be a absolute minimum, is because it is the very lowest point on the graph out of all the points here.
Mm-hmm.
B and C, I said neither, just because there is a jump, or there's a jump in the graph. It's neither like going up or either a concave up or a concave down. D, I said would be a local minimum because it's not the very lowest part, but it's also a concave up. R, I said, was an absolute maximum just because it is the very highest point in this section. S, once again, is a local minimum. It's not the very lowest, but it's also a concave.
Yeah.
Yeah.
So I think for was it S was the last point? I think that she said that wouldn't be a local one because you can't go to the right and see anything.
Possibly. Whenever I look at graphs like this, I always use my imagination because I see like this is already going like that and it's looking to be curving up or straightening out. So
Yeah. I mean, that's what I thought before she said that in class, but then she said that and I was like, oh. So I don't know what that would be called then, but I do remember her saying like I think there was an example we went over and she was like if you can't look to the left or right and it's just like over one side, then you can't classify it as a local.
makes sense. I can do a double check in my notes in the book again.
Okay.
Yeah. But other than that, it sounded great. I think you're right.
Yeah. The others were good.
Yeah. Awesome. Are we on our applies now?
Yeah.
Yeah.
Awesome. switch over here. Share my screen. So for my apply, I attempted to do number 70, which asks, I'll just read off the whole thing. So an object with weight W is dragged along a horizontal plane by a force acting along a rope attached to the object. If the rope makes an angle theta with the plane, then the magnitude of the force is F equals that little U looking thing is the coefficient of friction times weight, and it's going to be divided by the coefficient of friction sine theta plus cosine theta. And it says where the coefficient of friction is a positive constant and theta is going to be greater or equal to 0 and less than or equal to pi over 2. And then show that F is minimized, or force is minimized when the tangent of theta is equal to the coefficient of friction. So my instinct here was to just try and take the derivative, because it's going to have to be, like, the force is going to be minimized when theta is going to equal 0. At least that's kind of what I thought. So then I tried taking the derivative of it, and that's pretty much as far as I got. I didn't really know exactly how to do it more than this, and I treated the coefficient of friction as a constant. I underlined it here because it says a positive constant, so that's what I treated it as during my differentiation here. And this is just what I got. But I know, I mean, I didn't full prove that force is minimized. So not quite complete, but that's just as far as I got for getting stuck. I didn't really see where else to go from here. And that's it.
So right there with the derivative part, that's just making it so you're not getting like something over 0. It's those what are they called again? Like it's
In
fine.
indeterminate form.
That's the one. Form. So you're on the right track. There's just more that you got to do with it.
All right. Yeah, I'll have to go back and rewatch her video on this section. See if I can get any helpful tips there, and just try to keep moving through.
All right, so I did number 72 for my apply. All right. So it's talking about a space shuttle that was launched and just the different like stages it goes through. Time at like after time in seconds, and then the velocity after that time in feet per second. So it says to enter this data table here into a graphing calculator, which I did, and then I did a cubic regression on the calculator and got my polynomial, which is going to be this here, 0.00146 x cubed minus 0.1155 x squared plus 24.98 x minus 21.2687. So that was part A, was just to find that equation for that and then graph it also. So I've got my Desmos graph here. I kind of zoomed out so you could see. Actually, I don't know if I zoomed out enough. Yeah, it looks like I've only got like, oh, actually I might have, but you can see kind of the general idea of where it's going on the graph. And then part B was to find the model for acceleration of the shuttle from t equals 0 seconds to 125. So I just took the derivative of my first function, which was going to be the cubic velocity function, and got my acceleration function there. And then estimating the maximum and minimum values. So your minimum is going to be, of course, 0 feet per second of acceleration, because at 0 seconds it's not moving. And then I plugged in the max, which was going to be at 125 seconds to this equation, and I got that the maximum acceleration was going to be 64.5425 feet per second.
Alright, I
Yep.
think I have that.
I did not do that one yet, but it looked right, and with your cubic regression there, with the all the points plotted, and it seems to follow your scatter plot pretty well. So
Yeah. The only thing was, like, when I zoomed in all the way, it like wasn't hitting the points totally, so it scared me off a little bit. But like
yeah,
it
well,
said to use the cubic regression, so I
yeah,
assume that's what I was supposed to do.
yeah, because it's not going to be like exact, it's just going to get close. It's more like a guess,
Yeah, that makes sense.
Okay, so I also did 70, and I don't know, it was really complicated.
Yeah.
So I'll try to explain it well, but so yeah, I started out the same way. I took the derivative, and then after taking the derivative, I set it equal to 0. And let's see, after setting it equal to 0, kind of just simplified it, and then after that, you can figure out that the weird looking u, I forget what it's called, is equal to tangent. And then after that, you go back to the original equation and you set it equal to 0, or yeah, you figure out what f of 0 is and f of pi over 2 is, which is, the square root of u w, or times w, and then just w. And then after that, you plug in the u for tangent into the original equation, and then you simplify the equation because in the bottom you have the tangent times sine plus cosine, which becomes sine squared of theta plus cosine squared of theta over cosine of theta, which is just and then you take that and you like flip it and you multiply like the w tangent of theta by it, and it simplifies out to just being w sine of theta. And then you make this little triangle so you can figure out just from the problem like what it's actually asking. And then you figure out that sine of theta equals the square root of u over the u squared plus 1. And so then you go back to the original equation, and or you don't go back, you go back to the simplified version where you already plug tangent in, and so then it's just w times that, because you just plug in that for the sine of theta. And then basically after that, it's just saying like it's less than 1 and less than the u, and with the w it's less than w and less than u times w. And basically from just proving that part right there, you can say that the absolute minimum of f equals square u w, or times w over u sine of theta plus cosine of theta is the uw over the square root of u squared plus 1, which occurs when tangent of theta is equal to the square root of u.
all
So
right. So for mine, I just kind of need to simplify it, set it equal to 0, solve for theta, and just keep working through the problem there to figure out the like the minimum it can be within its given like domain and the maximum, and then just to prove that that force is minimized.
Yeah, I think you just
Okay.
like ended up getting confused on what you were actually supposed to do.
Yeah. All
So
right.
it took
Yeah.
me, yeah, it just took me a while to figure out what I actually needed to do. Because once you figure it out, like the math isn't that complicated.
Yeah.
It's just knowing what you're
I'll
actually
have to
supposed to do.
relook at mine and see if I can figure it out with this new information.
Yeah. I mean, I feel like once you know like the direction you're supposed to go in, it makes it a lot more simple to figure it out.
Yeah, because these apply problems are mainly just to teach us how to pick information,
Yeah.
only like the useful information out of what you're gonna need to get with it.
Yeah. They're definitely a lot more complicated in that way.
I also did number 70, and like since it was already explained very well by Eli, I could just help, I guess, show parts that you would have to look at, Brandon.
All right.
Simplifying for f of 0, because we're looking at the endpoints 0 and pi over 2. That's how you get your w and w by itself. Once you have, once you find those, knowing, I guess, like your endpoints, to substitute tan of theta for u, you just have to remember your trig identities. Basically, get rid of everything. Maybe with that w sine of theta. Since we're looking at these two endpoints and it's not in the whole word scheme, it's in the actual numbers. That's why we had to use the triangle. Triangle for sine is 1 square root, or yeah, the square root of these two squared, just for the endpoints. And that's, since sine of theta isn't the whole thing here, it's the whole u. Just gotta put in that you found. Yeah,
Yeah. All right.
the exact same thing.
Well, it definitely looks right. I'll have to go back. Thank you for the input. All right. Now we're on 4.2. Play. Go ahead and share my stuff. So for my 4.2 play, I chose to do number 1. And number 1 says to verify that the function satisfies the 3 hypotheses of Rolle's theorem on the given interval, and find all numbers C that satisfy the conclusion of Rolle's theorem. So, well, the first thing I did is just to verify that the Rolle's theorem can actually be applied here by stating right off here to the right here. I state that f of x is continuous on the closed interval of 1 to 3. I state that f of x is differentiable on the open interval of 1 to 3, and that I actually solved it, that f of 1 and f of 3 are equal to each other. So now I know that Rolle's theorem can in fact be applied here. So in order to satisfy this, I take the derivative of the original equation, which this is pretty simple. This was a very easy derivative to figure out. It's just going to be the derivative of 5 is 0, and then minus 12x is just going to be 12, and plus 3x squared is just going to be 6x. And then I plug in 1, I believe. Yeah, for my you just plug in the 1 for your equation. No, God, I'm sorry. You set it equal to 0. Sorry, to figure out when the slope is 0, there is a critical point there. That is what I did. So I just set the negative 12 plus 6x to 0 and then solved for x getting 2. So I know now that at an x value of 2 on my graph here, there is going to be a critical number, and that it is 2 is in fact in between my interval 1 and 3. I got mixed up there with my notes.
All right. So I also did number 1, but honestly, totally butchered it. I did not apply Rolle's theorem the right way. I don't even know what I did, honestly. But it makes a lot of sense what you were saying about applying, or just the way that you applied the theorem. So yeah, my work is just, I don't know what that is. But obviously finding that it's continuous on that interval, that it is differentiable. And then I got an answer here that was pretty close to your 2. I got -2. But just I didn't even take the derivative. I must have been thinking something else, um but yeah, for next time, then I would take the derivative and then plug in the 1 like you said, and then
Yeah.
find that it fits the interval.
Yeah, I'm not
Yeah.
quite sure what you applied there, but you
Yeah, I
got
don't know.
close. But yeah.
Yeah, I don't know. But anyway, that makes a lot more sense what you were saying.
Yeah. UI.
Yep. Oh, sorry. I also did number 1. Pull it up. Yeah. And I didn't do it, or I don't know. I don't know if I can explain mine as well as you did, Brandon. But basically, did the same thing. I didn't like write out that I actually like proved it. I just kind of like did the steps and hope she'd understand. Basically, like you have the original function, and then I set it equal to 1, and it set it equal to 3, and they both came out to -4. I took the derivative to make sure it's differentiable, and also that it's continuous. And then I set, or because I solved for that, we know that f of 1 is equal to f of 3. And then I just solve for f prime of x equals 0, and so solve for x there, which I just took that, and it came out to be 2.
Yeah, we did the same thing. I just kind of wrote mine more like directly with the words to like put
Yeah,
emphasis on the application of Rolle's theorem.
yeah, just to make it make more sense.
Yeah.
I was just kind of like going through and making
Yeah.
sure I had the bits and pieces rather than
Yeah. You did
focusing on
do all
explaining
the
it
steps
well.
though. You made sure that f of a is equal to f of b and that it's continuous on the closed and differentiable on the open interval.
Right.
Yeah. We did the same thing. Mine's just more like written out.
Yeah.
So in this case, it's only the 1 that you're plugging into the equation, right? And then the
Um
3
you
is there to like satisfy the theorem.
you plug in 1 to the original equation and 3 into the original equation to make sure that you get the exact same answer, like as you see that they're
Yeah,
both equal to -4. If that's
yeah,
true, and you can graph it on like you can graph the original thing on Desmos, and you can see as long as there's no like jumps or stops or holes, then you know that it's continuous and that it's differentiable. Then
right.
you can apply Rolle's theorem, which all Rolle's theorem is that it states that if those 3 conditions are true, then there is a critical number no matter what. And finding the critical number is just taking the derivative and then setting that derivative equation equal to 0.
Okay, gotcha.
Yep.
All right.
Right, and I did question number 9. Basically, it's just asking verify that the function satisfies the hypothesis of the mean value theorem on the given interval. Find all numbers of C that satisfy the conclusion of the mean value theorem. This is what it starts out with. X is equal to 2x squared minus 3x plus 1 over the interval 2. Work said first I had to find is f continuous on the interval, and said yes. Polynomials are continuous from negative to positive infinity. Is f differentiable on 0, 2? Yes, it is. Domain is continuous. Find c, so I'm going to take the derivative of the function. So f prime of c is equal to f of b minus f of a over b minus a. So c is going to be this little number right. It's going to be 4c minus 3 is equal to b2 minus f of 0, 0. You see the big equal signs is going on to the next equation. Find my value of c, which is just 1, since it's singular x on an x squared over this interval, comma 2.
Yeah, and that's for number 9, right?
Yeah, I think so.
Yeah.
Yeah.
Awesome. Which was pretty similar to the ones that we did, so
Because
it looks right.
yeah, it's like Rolls. How'd you say it? Rolls
Roll.
Rolls theorem.
Yeah, is basically the same thing as the mean value theorem.
Yeah.
They go hand in hand with each other.
All right. So for the apply on section 4.2, I did number 35. Let me go ahead and share my work. So number 35 states that two runners start a race at the same time and finish in a tie. Prove that at some time during the race they have the same speed, and it gives a hint. Consider f of t is equal to g of t minus h of t, where g and h are the position functions of the two runners. So what I did here is I stated the stuff because this is a proof, so I wanted to be as like direct as possible. So I said that g of t is equal to position of runner A, and that h of t is position of runner B, and that f of t is equal to g of t minus h of t, which is in our hint. And then I know that using like the derivative rules, the subtraction derivative rule is f prime of t is going to equal g prime of t minus h prime of t. So I wrote down that t of 0 is their starting time because we're in that, like that's like the initial time, which is their start, and then t1 is their finish time. And I know that they started and finished at the exact same time. And then I also know that using this here, the mean value theorem, like applying to this is g prime of t is equal to g t1, which is their finish time, minus g of t0, which is their starting time, all over t1 minus t0. And that's basically the exact same thing I did for the h prime for the different runner, the exact same numbers. And I know that sees that h t0 and ht1 is going to be the exact same thing as g t0 and gt1, because all it is the different runners. So h of t0 is just position of runner B at the start. So position of runner B and A at the start are the same, and at the finish are the exact same. So no matter what, I'm going to be using the exact same numbers for both of these. So I'm going to be getting the exact same result. and something minus itself is going to be 0, so I can say that f prime of t is going to equal 0. So therefore, a time exists, a time t exists that at some point they are going to be running the same speed, which is their whole thing here.
Yeah.
That's all it asks, is just to prove that.
Yeah. I did the same one, number 35, except I didn't write out like as many of the variables or like things like that as you did, which it's a proof, so maybe I should have just to like let it make a little more sense to other people and not just me. But I have basically here the f of t equals g of t minus h of t, and then just basically like those are going to come out to 0 since g of t also equals h of t out here. And that also goes for the derivative of f of t is going to equal derivative of g of t and h of t. And then g of t, or I mean g0 is going to equal h of 0, and then g1 is going to equal h1 because at the same point, these runners are going to have the same time at some point during the race because they're starting and stopping the race at the same exact time.
Yeah.
So, yeah, I just didn't quite write it out as much as you did, but I had the same
Yeah,
general
it's the
idea.
same thing, you know. I mean, if they start and stop at the same exact time and place, then you can just say that their average speed have to equal, you know, their averages have to equal the same, their average speed, and the average speed is just going to be the derivative. So their derivatives are equal to each other. So you can just
Yeah,
work backwards from that. But I understand what you're saying. It's the same thing, just more written out.
yeah, my whole thing here was just basically like since they are the same function, they are going to
Yeah.
cancel each other out at a point. So, yep. And then Eli.
Yep. I did 35, and I don't know. I did it like in a weird way. We'll get to see. I mean, it makes sense to me, but I don't know if it's the actual like mathematical way you're supposed to do it. It's basically 35. It's asking. Let's see. It's asking like two runners start a race at the same time and finish in a tie. Prove that sometime during the race they have the same speed. And so basically, my thought process going into that was if they both run like x meters and y seconds, just the same amount, it doesn't matter. Both of their averages speed are the same, right? X over y, whatever meters per second, or whatever it is. And so basically, using that, like I don't know if it's actually IVT that would prove that, but it's like the same thing. Basically, IVT proves like that if something's continuous and sometime between the beginning and the end, there must be like a value c where it's like proves that there's some value c that's where they're going the same speed. So I don't know.
Yeah, so it works like hand in hand with like the mean value theorem and rolls.
Yeah,
Yeah,
I knew it was something like that. I wasn't sure how to
how to
word
quite
it
write
like
it out.
perfectly.
Yeah, conceptually that does make sense though that their
Yeah,
average speed would be the same. So,
Yeah,
but
and
yeah,
so yeah, knowing that like the average speed is the same, you know that somewhere they have to be going the same speed, or else they couldn't have the same average speed because one
yeah,
would have to be like higher or lower.
exactly.
Yeah.
So I did a question 34, and it was basically the same thing, but incredibly more easier. I'll show you here. So my question was, at 2 p.m. a car's speedometer reads 30 miles an hour. At 2:10 p.m. it reads 50 miles an hour. Show that at some time between 2 and 2:10 the acceleration is exactly 120 miles per hour squared. So basically, you're just trying to solving for that c value, and since the time is 2 and 2:10, that's a sixth of an hour, which is why we're using 1/6 for this. If you take the b minus a over b minus a, it's going to be 1/6. You'd get 50 minus 30 over 1/6 the time, 20. So there exists a number c that 0 less than c less than 1/6, which is in that between the interval that we're trying to find. Prime c is equal to 20. I have to do the very last part of that mean value theorem.
Yeah. Now, honestly, the reason I didn't even do that one, I decided that 35 was going to be a bit easier, but now seeing your explanation of it seems rather simple. I should go back to that one soon.
They're basically the same thing where you're trying to find that like one point, but they're the same. Or in my case, I have to find it where they're exactly.
Yeah. Which, I mean, it gives you all the information you need. I mean, now that you've explained that to me, it's really just kind of straightforward from at the start to the finish.
Yeah, I think the 1/6 of an hour would have tripped me up. Like I would have been looking for what to plug in there, but
Yeah.
yeah, I'll definitely remember that now when I go back and do that one, because that makes it a lot easier. Because I was like 120 acceleration, like how is that possible if they're only going from 20 to 30 or whatever it is? But 1/6 makes a lot more sense.
Yeah.
Yeah.
Or how fast I go at any given second since I speed. I would never speed, but if I did.
But, oh yeah. And I think
Of
that
course.
just about wraps it up. Anything more to add before I end the recording?
Do we need to do our discussion craft or whatever?
You do the talk about our questions now, or we
Oh
can
yeah. We
brainstorm
gotta
after?
craft our questions in here. We don't we gotta pick out which questions you want to do,
Okay.
Yeah.
No,
and then
one that you were saying earlier about the wave, the length of the wave. That was in
wasn't that
3.11.
Or 3.11 apply
Yeah,
number
5,
48.
Oh yeah, right there.
Or I mean
Uh,
49, my bad.
Yeah.
It's a water wave with the length L.
isn't that
Yeah.
4.1?
No, it's 3.11.
3.3.0? Oh, okay. I had the wrong sheet.
So just
Alright.
basically like using it to measure like when a tsunami would be coming.
Yeah, like a
Yeah.
real life like
Tides.
application of that like could be with natural disasters.
Right.
Or like does the same equation or like same idea apply to like earthquakes or something like that?
Yeah. I feel like those are
Okay.
pretty good, pretty solid questions for that one. Maybe that
And
should
then
be our apply question for our team crafted questions.
sure. And
And
then
then
for play.
play. Um, honestly, we all did, not all of us, but three of us, right, did number 1 for 4.2, right?
Yeah.
Yeah.
I mean, we could probably just do that one, like how Rolle's theorem kind of goes with the mean value theorem, and you kind of use like the same properties of it.
Right.
And then like maybe like a question for that could be like what more applications could Rolle's theorem roll into, or maybe like what other conditions may apply if given more variables
Yeah.
to work with here.
Yeah. I think that'll work.
Yeah.
All right.
Who
Cool.
wants to do our question post for us?
I'm gonna be going right now 'cause I haven't eaten yet.
Yeah, I'm actually leaving here soon too. I don't know if I'll have time tonight. I mean, we have to like tomorrow too, so
Yeah,
Yeah.
I can probably do it. It's let me make sure I write down the questions though.
3.11, 49, and then 4.2, number 1 for play.
yeah,
Okay, so 3.11, number 49.
Yep, for
Yeah.
apply.
yeah, 49.
I'm looking at my notes right here about Rolle's theorem and the mean. And the first two parts, the whole f of x is continuous and f of x is differential, are the exact same. The only part that's different is the last part. For Rolle's theorem, you have to meet all three, where the last one is f of a is equal to f of b. But for the mean value theorem, you only have to meet those
The
two, because
first
there's
two.
only two conditions.
Okay.
And then, like, it says, like, if those two conditions are met, then f prime of c is equal to the f of b minus f of a or b minus a.
Yeah. All right. All right.
So maybe like what real life scenario would you be able to apply like Rolle's theorem versus mean value, or like what would you only apply one of them?
Yeah. I mean, it feels like Rolls is like more straightforward. Like if you're lucky enough for that third condition to exist, then like it's just so straightforward. You just take that derivative and set it equal to 0. But with the mean value theorem, it's if that last condition, if like the a
Does-
f of a does not equal f of b, then you can take the mean value theorem. You have to put in more work.
Mm-hmm.
Okay.
Awesome. Eli, you got those questions down?
Yeah. So for the apply, it's like the tsunami or earthquake or how it would
Yeah,
apply
like
to real
more
life.
natural disasters.
Yeah. And then for the play one, it's just like what real life scenario for Rolle's theorem versus mean value theorem, like how like
Yeah.
they apply differently.
Yeah, that sounds good.
Okay.
Awesome. There it is, guys. Are you guys ready for me to end the recording?
Yep.
Yep. We're all
Good
good.
stuff.